Hi there. Today we'll look at Descending Through a Crowded Valley, Benchmarking Deep Learning Optimizers by Robin M. Schmidt, Frank Schneider, and Philipp Henning of the University of Tübingen. So this paper is an empirical investigation, a benchmark into optimization algorithms for deep learning. The short story of the paper is use Adam, it's fine. The long story is a bit more complicated, and the resulting answer is basically we still don't know, even after this paper, if there is a single good recipe for optimizing deep learning, and if so, which one it is, and where it works and where it doesn't work. A lot of things are still unclear, and I think the biggest lesson from this paper is that probably the best thing you can do is pick Adam or SGD with momentum, tune it a little bit, and whatever comes out of that is probably doing okay. So let's dive into the abstract here, but first, as always, if you like content like this, don't hesitate to share it out and also tell me what you think in the comments. With this paper, we're going to see that there is a big room for interpretation here. So you're going to see experimental results, and the experimental results, they can always be interpreted in the light of different hypotheses that you have what's going on. And very often you have to pay careful attention that something like Occam's razor, that you obey something like Occam's razor. Sometimes people try to read a lot into their experimental results when a much simpler explanation would actually be sufficient. Not that much with this paper, but you're going to see a lot of results. They can be interpreted in a lot of ways. So yeah, tell me what you think in the comments. Happy to have a discussion about this and hear your thoughts. So they say choosing the optimizer is considered to be among the most crucial design decisions in deep learning, and it's not an easy one. The growing literature now lists hundreds of optimization methods. In the absence of clear theoretical guidance, and conclusive empirical evidence, the decision is often made based on anecdotes. So I'm just going to show you, they have actually a list in the appendix. They are tracking this optimization algorithm. You already see this is massive, right? So you have things in here like, Nesterov and Polyak, which are very, very senior in the field, but as you can see, a lot of algorithms popping up in 2016, 2018, 2019, 2020. And it's PolyAtom, Power SGD. And all of them have their respective paper. Yeah, SGD, look at that. Going strong, 70 years. So you can see that this is almost an impossible list of things to consider when you choose your optimization algorithm. And it seems like it's just getting worse. They have this graph over here where they count how many times each of the major optimization algorithms has been cited. 2020 is shorter because the year's not over yet. I was kind of surprised as well. Like, wait a minute. It can't be that our field is shrinking. This will never happen, surely. But it's just because I think the year isn't over yet, or wasn't at the point where this paper was written. But you can see the popular optimization algorithms are mentioned more and more and more. And also the non-popular optimization algorithms, they seem to multiply over the years, as we've seen from the list. So choosing one is hard. What this paper does is it doesn't compare all of them. So they choose a list of 14 different optimization algorithms. Oh, they also track these learning rate schedules, which is also ridiculous. It's like, oh no, but we don't do a constant factor decay. We do multi-step decay, and all of this makes all the difference. Remember that each of these papers sometimes it's just been suggested in a paper, but especially for the optimization methods, most of these papers are about the optimization methods, right? They are saying this is a new optimization method. It's good for either all of deep learning or a particular subset, particular algorithms or settings. and it's better than than everything that came before. Either it's faster or uses less memory or something like this. So all of these are papers that suggest some kind of new algorithm and show that it's better. Now, in their paper, you'll always find that their algorithm is better. And having read and tried to re-implement and so on a bunch of these papers, I can tell you that not a lot of the papers are, let's say, all of them in their experiments is of course better, but that's not a recipe for taking the optimizer and applying it to other problems. It always looks good in the papers, and that's why independent benchmarks like this are valuable. You see the decay rates for the learning rate or learning rate schedule. It's not always decaying. So here is the things that they actually consider. These are what they consider the popular algorithms. So you have things like add a delta, add a grad, atom. You have things like look ahead, momentum, which is SGD plus momentum. You have RMS prop, just plain SGD, and so on. And you can see each of those comes with its set of hyperparameters. So for example, in pretty much all the methods, you have a learning rate, which here they call alpha. And in the momentum, you additionally have the momentum term, which is here called, what's that, rho. Of course, in other methods, like in look-ahead random, you have a slew of hyperparameters that you can all tune. All these hyperparameters come with their default setting. And the authors here additionally define a tuning distribution over which they search. So I'm going to criticize this work here quite a bit. Remember, most of what I say in the criticism is actually acknowledged by the paper itself in their limitations, which is much to their credit, right? So just because I criticize it, it's very easy to criticize empirical studies, investigations, especially benchmarks, especially comparisons. Most of it is addressed by the paper, which is a very, very good. It's very nice for a paper to be honest about its shortcomings. And yeah, just keep that in mind. So the first criticism I have is what they're going to do is for each of those things, they're going to compare 3 settings. So in the first setting, wow, that's a big pen. In the first setting, it's one shot. So they just say, we are going to take the optimizer, let's say atom, and we're just going to plug in the default parameters for it. And we just let it run and see how well that does, okay? And the second is with tuning a little. So they call this, I think, the small budget, tuning small budget. And then the third one is the tuning with a large budget. And the difference is simply that you try more things in the large budget, and you take the best one according to your validation metric, and then you let it evaluate it on the test metric. We'll get to that in a second. My point here is that there's 2 things. So first of all, they do a lot of experiments in this setting 1, and they make a lot of claims about it. And this setting 1 is entirely dependent on the default parameters given either by the authors or by, let's say, popular frameworks, which often take them from the authors, which it's okay. Like most people are going to use it and use the default parameters. But I would argue investigating the default parameters in this kind of setting where you compare optimizers is kind of useless. What I would expect from a benchmark like this is to determine its own default parameters, like to determine, okay, what parameters are the best. Maybe you take, what you're going to see is they do a benchmark over different deep learning problems. You take half of them and you determine what single set of parameters works best on half of them, and then you evaluate, say, that's the default parameters for the other half, or something like this. Comparing just out of the box default parameters, it might just mean that the default parameters, the authors haven't really spent time worrying about it and simply released a bunch of code. And by simply changing the default parameters, you can improve it. You're going to see that. The second one is here over the tuning ranges. So for each of these, the authors define tuning ranges. So ranges where these tuning algorithms are going to search over. They are going to do random search. And here, for example, this is a log uniform distribution, the LU. So it's going to search from 10 to the negative 4 to 1, which of course is 10 to the 0 in log space. So it means it kind of samples the exponent on a uniform scale, and then it plugs that in, which is, good. That's how we do it in research. However, compare, for example, you have something like Adam, where the default parameter is 10 to the negative 3. And you have something like momentum, where the default learning rate is 10 to the negative 2. Yet the range here is the same. And they make this clear. They say when the authors don't give a range to search over, we simply take over the range from what is commonly done for that parameter, or from a different method. Which you can see that 10 to the negative 2 is exactly in the middle of this log uniform range. However, 10 to the negative 3 isn't. So when you already make the case that you use the default parameters, you really, I think, have to make sure that the range you search over, the default parameter is kind of in the middle of that range. Otherwise, your range is kind of not according to the default parameter. So that's kind of already slight criticisms of this paper, and you can already see. I'm not telling you that to trash the paper. I'm telling you this is extremely hard. Like, to benchmark optimization algorithms with hyperparameters, with different hyperparameters, with different amounts of hyperparameters is super duper hard. Okay? Like, everything influences the results here. What the default parameters are, what the ranges here are, how big the ranges are, right? If you make them too big, your search is going to spend a lot of time in regions where nothing's happening. How often you search in them. So let's say what a lot of people do in Adam is they keep these constant, but they just tune the learning rate a lot. So how much you tune each parameter is important. How many parameters there are is important. All of these things, like if you have to search over 4 parameters, it's going to be much noisier results than if you just have to search over 2 parameters and so on. So this already, as you can see, is a hard task. And this says nothing yet about the learning rate schedules that they also try. Where is it? Okay, they try 4 different learning rate schedules, which again can be tuned, though I think they don't tune them here. And they do so on 8 different problems. So there are 8 different problems. Where are they listed? Right here. There are 8 different problems. So you have what they call small models over here. These are like artificial data, quadratic, noisy quadratic, a small MNIST VAE, a small convnets, as I understand it. And then you have what they call large problems, which is a CFAR 100 CNN, SVHN, a character RNN, and so on. You might already notice that also in this department, in the problems department that they search over, these are very particular kinds of problem, and that they acknowledge this as well. There's like no reinforcement learning, no GANs, and so on, and they are not that big. Even the large ones, they are kind of small. And of course, they are doing grid search. You know how much compute they spend doing this benchmarking stuff. You can't benchmark models like GPT-3. On the other hand, we know for a fact that there are effects of scale that there is a qualitative difference between large models and small models and ever larger models. You can't simply extrapolate from small models because they have very different properties. It's also a relation to how big your data is in relation to your model. So my kind of criticism here is that we are searching. Oh, here are the problems. Yeah, you see that there are 8 problems. The bottom ones they call large, the top ones they call small. We are searching over a very small subset of deep learning problems, namely, and this is something I pointed out already, I think, a few videos ago. Let's consider all of these things small models compared to something like ImageNet model or a big translation model or something like this. Let's consider these small. If I have a small model, I can do grid search, no problem. I can tune. I can try out all my optimizers. If I have a if I have a large problem, I can't. Yet these studies, they only tell me something about small models, and we already know it's very difficult to extrapolate from small models to large models. We know that there are effects in batch sizes. New transformer models on TPUs train with batch sizes of 4,000 or something like this. The epochs, we know that, for example, self-supervised pre-training train with much higher epoch counts than classic supervised learning, and so on. This tells you something about a very tiny subset of problems, about a tiny subset of optimizers on these particular problems, and it is highly dependent on how you exactly set up these experiments. So we finally go to how they combine this. We've seen what optimizers they choose, and we've seen what problems they apply them to. So how do you select an optimizer? No, where was the thing that I was going to? Yeah, so when they tune, the one-shot setting is they just take the default parameters, which I already said I criticized. You should determine good default parameters over all problem, and that be the default parameters. And then, but I guess they go after what people do. People just plug it in, and first thing they try is the default parameters. So, yeah. What they do is when they tune over these ranges that we've seen. They say we only use a single seed for tuning. Okay, so they set the random seed of an experiment to a particular point, and then they tune, for example, the learning rate, always starting with the same random seed. And they look at the validation loss for that random seed, and then once they have the best learning rate, they repeat the best setting 10 times using different seeds. So they tune. Tuning is done in a single seed, but testing is done using different seeds. Okay? They say right here that progressing this way has the feature that our tuning process can sometimes pick lucky seeds, which do not perform as well when averaging over multiple runs. This is arguably a good reflection of reality, which is true, right? But the inherent problem here is that, so what's the danger? The danger is that you have a loss landscape, whatever, and you start maybe here, okay? That's your random seed where you start, and you tune the different learning rates, like going down, down more, down, that's too much, and so on, okay? So when you start there, one algorithm might look very good, an algorithm that is suited to starting at the edge of like a cliff, but only there. Like that algorithm might perform very poorly anywhere else in the landscape. So this is your tuning seed, and you tune that, and the learning rate and algorithm you determine are performing fairly well, and then you take that same setting, that learning rate you determined, and you start it from different places, right? From here, from here, from here, from here, and all of a sudden, this performs very, very crappy. However, a different learning rate might have done, or a different algorithm might have done very, very well. So maybe for the red one, you determined a small learning rate is actually pretty good because I'm right at this edge of a cliff, and the small learning rate, prevents me from going there. And the small learning rate looks pretty good in the validation loss. But then you start from here, and the small learning rate, it does nothing from here. It just blows. And so you get what I mean. You can get very unlucky in this tuning seed. And while it's true that this is correct, this is happening in the real world, this is not suitable for a benchmark, right? So keep in mind that these benchmark results, it could just be the entirety of a test outcome for a given algorithm could just be due to the fact that the tuning seed was crap. Because even though the test runs are averaged, the tuning is done on one particular seed. Okay, I would argue, they say, yes, if we used all 10 random seeds for tuning as well, it would drastically increase cost, not only for this benchmark, rendering it practically infeasible, but also as an approach for the practical user. Look, I agree, but this is not like, it's really necessary in something like this to use different random seeds, because what you want to show in the benchmark is how this algorithm is doing on average, right? Because the benchmark is supposed to inform future users. However, right now the benchmark is like a single user that can be lucky or unlucky, right? It's not informative. And I see the point. What they're saying is that it would make this benchmark infeasible. However, it doesn't change the fact that it's necessary in the benchmark. Any experiment that you do is like a fraction. Okay, the fraction down here is cost, and it's like dollars spent or time spent or whatever. And the fraction and the numerator is going to be maybe something like information. The information that you gain from an experiment. Now, what there are, not all experiments are the same, right? You can't just say, well, we use as much cost in our experiments as the people who invented ResNet, right? Maybe you do that. Maybe it's actually true. Maybe they actually use more because they do this giant grid search. Like, our experiments cost more than ResNet's, so therefore they should be respected even more than the experiments who figured out ResNets. Which is not true, because you have to pay attention to the numerator right here, which is the information that you gain from an experiment. And if you do it like this, yes, your cost is lower, but your information goes towards zero, in my opinion. It's not zero, but it is very small, because you have this one seed per algorithm that you bind everything to. So the entire benchmark can just get lucky or unlucky with a particular algorithm. Okay, so that is kind of my biggest criticism with the tuning right here. So let's go into the results. I think enough me brabbling about the setup right here. They have these deep learning problems. They have these 14 algorithms. The learning rate schedules, they come in later, but they're not really prominent in the benchmark. What they do is they compare the algorithms with the default parameters, with a small amount of tuning, and with a large amount of tuning. And this is one of the main results right here. Let's actually look at this particular thing here a bit more. So what you see as the way you read this is these numbers represent algorithms. You can see it beside them, but you can't see it down here, but they represent the same algorithm. So 1 here is AMS bound is also 1 here. On the left, on the y-axis, you have the one-shot performing algorithms, and on the x-axis you have the same algorithms if they are given a small budget to tune. So if we analyze one of those, for example, let's go numbers number 4 and 5. So number 4 and 5, number 4 and 5. So 4 is add a delta and 5 is add a grad. What we can say, if we look at, for example, let's look at this number right here. we see that, what's this, 5? Number 5, so add a grad is 40% better than add a delta when it is given a small budget to tune. So when add a grad is given a small budget to tune itself, it is 44% better than add a delta when it is not given a budget to tune itself. All right, I hope that kind of, so we compare having tuning budget to not having tuning budget. And this is the absolute test set performance improvement after switching from any untuned, from any untuned optimizer to any tuned optimizer. So the y-axis are the untuned and the x-axis are the tuned. And you already see a lot of kind of different effects right here. So you see that sometimes, which is interesting, in the red right here, these are negative numbers. So sometimes an algorithm, even given a small budget to tune, is actually worse than a different algorithm when doing the default parameters. And this is on one of these small problems, on one of these small CFAR10 problems. Okay, so that's one interesting thing, but I would argue it's actually not that meaningful for reasons for which I'll get to in a second. The most prominent thing probably you'll see is that there are rows that are kind of colored very uniformly. So you have, for example, this row, which is solid green, and then you have other rows which are, very either light or even red and so on. So what's going on here? What does a solid green row mean? Especially look at these high numbers like 45, 43, 43, 44. So this is performance improvement. It means that add delta is, when not tuned, is this much worse than any of the algorithms if given a small budget. So its default parameters suck badly. Okay, that's the message right here. If you see like a solid green row, the default parameters of this method suck badly. Okay. Now, as I said, what the value of this is, actually maybe this is the most valuable thing that comes out of this benchmark, honestly, because everything else is so noisy, right? In theory, I would say this is the least valuable thing, because let's just, get good default parameters for all this stuff and then we're done. But apparently this is not done yet. So the delta's default parameters, at least given in the paper, apparently they suck. So does momentum, though. Does Polyak give, or Nesterov, whoever invented it, give momentum default parameters? Maybe. Maybe those were different times. Certainly didn't give default parameters for deep learning. But you see, again, they like the default parameters suck. What is also interesting is to look at the diagonal. Okay, so the diagonal shows you how much the same algorithm improves if given a budget. Again, you can make an inference about the default parameters when you say, okay, add a delta improves over itself by 40% if just given a little bit of budget to tune, while add a grad is only improving 2.3%. There are situations in other graphs where there's actually a negative values. You can see, for example, right here, there is a negative value in a different problem in the CFAR 100, and they can show in the appendix that this is due to not enough tuning. So basically the tuning is just a random search, and the random search is, again, the random search is so bad that it doesn't even hit any sort of setting where the default parameters are present. So all its search space is basically bad parameters, which again is, you can say that the algorithm is not really robust to parameter change, but you can also say that this is entirely due to the choice of search space to search over. So you can see that the algorithms 5, 7, 8, and 13 are particularly bad at this. Here we see that's Adagrad, LA, 13, what, RMS prop, yeah. But then if you look at other problems, you see that different algorithms, okay, the number 7 here is also kind of shady. So look ahead seems to be kind of shady in general. But this also switches from problem to problem, which is something I already introduced. There's a lot of noise here, a lot of noise. And therefore, yeah, what is a bit harder to parse out is how the algorithms compare to each other. So in order to determine that, what you have to do is you just have to look at relative performance. So for example, take any column, for example, this column right here. You see that no matter how high the number is, it's always a bit smaller than the rest of the row. Okay, so in every row, this is smaller than the rest of the row, which means that number 4, what's number 4? Add a delta. When you tune add a delta, it compares less favorably to all the other algorithms than when you tune other algorithms. Okay, so in order to really compare optimizers to each other in this graph, you have to kind of do this relative math in your head. And that's why I'm saying the negative numbers aren't even that important as long as they're not on the diagonal, right? If they're on the diagonal, they mean if you tune the same algorithm, it's worse than when you just run the default parameters, which just means that your search sucked. Or your random seed is somehow lucky or unlucky. What do I know? But the negative numbers off diagonal don't mean anything. That the fact that they're negative, because what you would expect is that the small budget always increases, at least in expectation, over the one shot. Okay. The question is then, how much would you expect it to increase? So even though a number like 0.3 here is a positive number, which means that the small budget number 2 improves over the one shot number 11, this could still be a bad thing, because you'd say, well, if I give you a small budget, I expect any algorithm to improve like 2% or 3% or 5%, something like this. Right? That's why you have to look at the relatives with respect to the other algorithms. You can't really look at the absolute numbers right here. So even the negative numbers don't mean anything, because 0 has no meaning here except on the diagonal, because you would always even on the diagonal, you always expect some kind of improvement from tuning, and we need to know kind of this average expected improvement before we can make judgments about the numbers in here. What you can see is that some algorithms clearly underperform with respect to the others, at least in this particular problem. Again, this is highly problem dependent. So I'll add a delta, pretty bad. Then what's this right here? This is 4, 5, 6, 7. Again, look ahead with momentum. Look ahead momentum, pretty bad. And you can find others. And this, again, varies from problem to problem, though numbers 4 and 7 are pretty bad here. Numbers 4 and 7, here also 5. Yeah, so you kind of see that you can make some conclusions about these problems, but here, look at that. So here they now include the schedules. And here you start out one shot with a constant schedule. If you add some of these schedules, it goes up a little bit. This is the median, right? And this orange stuff is the, what is it? The 25th to 75th percentile. Like, look at the amount of noise right here. So when you see these plots, it's just, I feel it's quite helpless, okay? Again, when you look at these plots, so what they give you right here is the red bars are whatever atom does when it's tuned. So when you tune Adam and then let it run over these 10 different test seeds, this is the range it gets. And the other lines are simply the mean across the other optimizers when you tune them. You can see just from the spread of Adam that the order in which these lines appear mean almost nothing, except here when they like crash like horribly. It just probably means that these optimizers, some optimizers just aren't made for some problems. But other than that, the order here is kind of useless. And you see the downward facing triangle is always untuned Adam, which in most cases performs fairly well compared to the others and compared to the noise you have over the different tuning outcomes. So that's why I said at the beginning, use Adam. It's probably fine. Tune it a little bit. If you realize it doesn't work at all, then switch to something like SGD with momentum. Or the other way around, right? Use SGD with momentum. If you realize it just screws up, maybe try Adam. And that's actually a thing they say as well. So one of their conclusions is that instead of tuning a single optimizer, tuning helps about as much as trying other optimizers. And they repeat this point throughout the paper. It's instead of trying a different settings for a single optimizer, you can get the same kind of outcome by simply trying a bunch of different optimizers in their default settings and then picking the best one of those, which it's, the entire literature seems to point to whatever you do, it's probably fine if you take one of these generic algorithms and kind of do whatever to select a good thing. Let's assume for a minute that all of these algorithms are the same and you simply change the algorithm instead of tuning the learning rate. Well, these algorithms come with different default learning rates, right? All these algorithms come with different default learning rates, and the learning rate goes into the algorithm in a different way. So the effective learning rate, even if I put in the same number, the effective learning rate is going to be different for each algorithm. So maybe what their effect here, when they say it's the same when you tune the parameters or when you simply pick a different default parameterized optimization algorithm, maybe what you're doing is the same thing. Maybe all these algorithms are actually kind of the same. And overall, right, for a particular problem, it's different, but overall, they're kind of the same. And when you pick a different algorithm, you simply pick a different learning rate for the same algorithm in disguise, because the learning rate, the default learning rate for that algorithm goes into its formula a bit different, and ultimately, you're simply tuning as well. So the benchmark is extensive. Again, I don't want to rag on this paper. The benchmark is super extensive. They also do rerun stability and so on. But this paper shows that it is possible to do an extensive search, extensive benchmark that is still largely useless. And I don't want to say that because they what I don't want to say is they didn't determine a clear winner, therefore it's useless. That's not what I'm saying. I'm saying the information content that I can get out of these experiments, especially for situations where it would help me, like for where I can't do grid search, is close to zero. I think the two big things that the community can learn from these papers is, one, the default settings for some of these things are crap in the papers and maybe in our frameworks. So maybe we'll go over that once more. And two, is like at least on these small kind of problems, it seems not that important which algorithm you pick. Pick one that you like, tune it a little bit, and you're probably good to go. If it doesn't work, pick another one. So that was it for this paper. Again, tell me what you think. What worked for you? If you have horror stories with optimization algorithms, they used to be much more prevalent. I think also our advances in architectures have made it easier for optimization algorithms. So like something like ResNet, giving you really nice gradient flow, has made it much more easy to optimize the network as a whole, and therefore the optimization algorithms aren't as important. And the last comment I want to make here is that a lot of these papers, as I said, they deal with specific situations, like, oh, if you have low memory, or if you have that, or they say our algorithm is really good, but only if you add like a bit of Gaussian noise on the input, or only if you use this very exotic learning rate scheduler or something like this, which this paper, of course, hasn't done. This is still a very small subset. So yeah, these are common criticisms for benchmarks. I think we'll take from it what it is. It is a cool paper. It is extensive. They are very critical of themselves. And that was it for me. Bye-bye.